Okay, so again, my name is Jean-Philippe Faure. I'm CEO at Progilon. This is a consulting company. So today I'm consultant for Panasonic. I'm chair of the IEEE 1901 working group. I've been the chair for years, and chair of Nessum technical working group and strategy and marketing working group. Okay, so this is the overview of standardization of the Nessum technology. So here, this is FiMac, basically standard, which is standardized in IEEE. So we have the original standard is IEEE 1901. It's been approved in 2010. And then you have several amendments. So amendment A, B, and C. So C for underwater communication, as I learned today. And I will explain all these things. On top of this, we have a layer 2 routing protocol on top of the FiMac, which enable to extend the range of communication. And I will explain also about this one. Next one, please. So I will focus first on the original standard. Next. So the original standard, again, was approved in 2010, and it was a single channel wavelet file. So operating, you see, in the band 1.6 megahertz up to 31 megahertz. And so it's wavelet OFDM. It's not a 50 OFDM, it's a wavelet transformer we use for that technology. And it's using 512 carriers. The main application at this time, remember the old days, it was Ethernet adapters. All the Ethernet adapters you have in retail, you know, to extend Wi-Fi or to connect to your IPTV and things like this. It was the main market and the main application at this time. Next, please. Then we made amendment A to improve the distance, to provide high speed and flexible channel. Next, please. So this is amendment A. So we added other channels to A. So if you see channel what we call now X1, this is the legacy one. So this is a channel specified 1901 2010. So we keep, of course, that one. But you see that we extended the number of channels. And we are extending it in two different ways, okay? We reduce the carrier spacing, or we increase the carrier spacing, depending on what we achieve. So here is the original carrier spacing. Here, if you multiply the carrier spacing by 4, basically we have a large channel, and you can increase the speed and go up to 1 gigabit per second. The original one was 240 megabit per second. The opposite way, if you reduce the carrier spacing, basically, so you have a narrow channel like this, still you keep the same number of carriers, okay? You just reduce the carrier spacing, and then you have less throughput, but higher range, higher distance, longer distance, because you focus your energy on a smaller spectrum. And so this is what we achieve: 120 megabits. When we reduce by 2 the spacing, and when we reduce the spacing by 4, we reach 60 megabits per second. So the whole idea about this is to introduce flexibility depending on the application. Some application you want to have high throughput. Example for coax9. If you want to connect cameras, okay, IP cameras, you can reuse the coax9, use Nessum technology, and you can have up to 1 gigabit per second. So one typical use case it is that you want to change your analog system, the old one, coax with peer-to-peer communication. You can use several IP cameras on the same tracks. So you increase the number of cameras, you don't change the infrastructure, same cable. And then you can mix different streams because you have the bandwidth to do this. This is a typical example. On the other side here, with a small channel, again, it is mainly to extend the range. And I will explain in the next slide. Here we have 1 minute. Sorry, if you can come back. Yeah. Here, just about this, we have a limit for power line, which is 100 megahertz. Okay. All above 100 megahertz, you cannot use on power line because of regulation. Yeah. Next, please. So this is a simulation on the cable to understand the impact of reducing the channel width. So basically reducing the carrier spacing. So the blue line is what we achieve with a standard carrier spacing. So you see that basically, okay, you have still 5 megabits per second on 400 meters distance on the cable. But if you change the spacing, okay, you reduce the spacing by 2, and you see that you have less throughput at maximum, but here, the limit for 5 megabits, it's around 700 meters. And if you divide again the spacing by 2, so the narrower channel, again, the maximum throughput reduces here. But here, you can reach about 1 kilometer on this. So this is why we introduce this, to get flexibility on what, depending on what you want to achieve. Next. The other dimension of flexibility is about attenuation and noise. Because if you remember the first mapping of a different channel, we can reduce the carrier spacing, and also we can select in which spectrum do you want to have a channel. Because in normal power lines, attenuation is higher with frequencies, with higher frequencies. If you look at this chart here, when you go to high frequencies, attenuation is higher. The attenuation is lower when you use a lower frequency. So also, it allows you to, depending on the channel, to use the channel if you want to have a long range, or if you want to, for another reason, to use another one, you can select on this. Again, about noise. So this is a typical case, but it's not always this. Typically, there are more noise at lower frequencies than higher frequencies, but it could happen is different also, because it really, depends on the application. And the different channel we have enable to select in which band you put the channel to avoid the noise, and then to increase your capacity, your communication capacity. So this is all the dimensions of the flexibility we have in the technology. Next slide, please. So this was 1901A, and it was in 2019. Then we made another amendment, which is 1901B, and it's focused on authentication. So basically, all the purpose was how to use IEEE 802.1x, which is a popular protocol for authentication, and how to use it with 1901 technology. Next slide. So this amendment was approved in 2021, and it explained basically, well, this is Wikipedia, so this is not specifically to Powerline, okay? This is just the way authentication works with 802.1x. So basically, you have an authentication server somewhere, and you use a radius protocol between your network and the authentication server. And when the supplicant basically asks the authenticator, which asks the authenticator server, and back to the authenticator, and back to the supplier. So it allows basically, it's very popular mechanism used in many networks to authenticate devices, and it's a good protection to you, because basically no one can join your network if it's not correctly authenticated. So it's a security feature, because nobody can spy, nobody can join, it's protected. So again, it's standardized and explained in 1901B. Next slide, please. And the last amendment is 1901C, so it's been approved this year. And there are 3 different aspects about this one. We include clock synchronization, so time precision protocol to support. So this is more for industrial applications like smart manufacturing, because you need to know the clock exactly. And we explain how to support this. We also introduced new channel with some other improvements of the channel, and also we made it available for any media. Up to 1901B, really IEEE 1901 focused on power line communication. And then in 1901C, we expanded to other media. Next slide, please. So 1901C, again, was approved in 2024. So it's an external flexible channel wavelet file layer. And you see, so these are 1901 channel as a reference. And we introduced even less carrier spacing. If you remember, in 1901A, it was 1/2, 1/4. And then we even reduced more, up to 1/32. So now, the smallest channel is less than 1 megahertz bandwidth. So it's broadband, but it starts to be some kind of narrowband now. It's close to narrowband because 1 megahertz is very. And of course, also, you don't need the full channel to operate. If you have 50% of the carriers on the channel that you cannot use, you still have connectivity. So it means that you can run this even in smaller channel than 1 megahertz. And again, you have the choice between different frequencies. So you can decide which frequency to use. So it's even more flexibility and longer range again. And again, same, we keep same modulation, same number of carriers. It's just changing the spacing. Next slide, please. So what's the purpose of this? So the purpose of this, the reason why we made a very small channel, was primarily for underwater IoT system. Because underwater requires specific frequencies. If you use high frequencies, propagation is not good. So actually, attenuation is so strong that basically you cannot reach even some machinery here, a few meters, and it doesn't work anymore. So then we had to reduce the channel width and also to go to lower frequency bands. So typical application is underwater drones or some robots. Also, for example, dam inspections, or well, there are a number of applications. So you put an antenna here, and the antenna undersea communicate with the devices undersea. But also, we basically can use Nessum technology on any type of thing. So power lines, of course. Should it be AC, DC, non-energized? Actually, you just use because you have a physical connection. You don't need the energy on it. You can use it on the coax cable, signal cable, twist pair. You can, with a proper interface, also use with optical fiber. And then we have also something. And even with light. You just need to replace the interface to the medium. Again, we support 1588, IEEE 1588 precision time protocol, which is one of popular one in smart manufacturing. And again, the market need was IoT, smart building, smart city, smart grid, and also including underwater using radio wave. So here we have an illustration of in building, you can use in elevators. In elevators, there are some cables connected into elevators, so you can use power line. Well, there are many, and here it's more about IoT and smart city. So this is about 1901C. Next slide, please. Okay, so I talk about FiMac, and now I will talk about multi-op, which is on top of FiMac. So here it's about basically to repeat, to route the packets on top of FiMac. So next slide. Yeah, sorry, come back. I forgot to mention. This is ITUT G9905. So it's standardized in ITUT under this number. So here, what is multi-op? So it's a relaying communication packets to enable long distance communication over several kilometers. So it's a maximum of 10 ops. So the longest route here is 10 ops. So the message is repeated 10 times over the tree. Yeah. And it's up to 124 terminals. So you can build with this quite large networks, actually. It's really target for large network. So remember the early days, it was Ethernet extension, Ethernet adapters into the home. And now we are talking about 124 devices and kilometers. So the scope has really changed. The market has completely changed. Next slide. So what's the advantage of this protocol? The problem with this kind of protocol is two things. Is overhead first, because all routing protocols, you need to discover the routes and to weight the quality of all the routes. And it creates a lot of message, because you have to send information to evaluate the quality of communication between each node. So imagine you have 1,000 nodes. Imagine all the routes you have to test before making the determination on which one is good to go from A to B. And this protocol has been designed specifically for this. And more than this, additional complexity, it is that one link between two nodes, there's one quality in one direction and another quality in the other direction. It's not the same. If you communicate from two nodes, A to B, sending the information from A to B, you have a quality, but sending the information from B to A, it's a different thing. It's not the same channel. So you have also to evaluate in their direction. And this is what's the protocol here. And so if you use a convention method, it's perfect. Huh? There are many methods, many routing protocols. But you see that the number of packets overhead increase drastically with the number of nodes. So it works with small networks, small number of devices. But when you want to reach 1,000 devices, you create more traffic about determining the route than really using the route for the user. So this protocol has been designed to reduce the overhead per node. And this is why it's suitable for large networks. Next slide. Then we have to care about two things, is unicast and broadcast. So unicast is something, but broadcast is another also big problem. In large network, broadcast could create a lot of traffic and congestion. If you have 1,000 nodes, you repeat, and then you overload your system. So this system has been designed to limit the number of relays for broadcast information. And broadcast is sometimes useful. Most of the time you use unicast, okay, because you have to tell one information to a specific device. But sometimes you need to send the same information to all the devices. For discovery, for instance, this kind of thing, you need a broadcast. So this is specifically addressed in this protocol. In unicast, the strength of this protocol, it is that it maintains the optimum route, okay, on the fly. So if the condition change, the routing tables are updated. And it's updated real time, and this point is very important, it preserves alternate route in advance. So it means that if for some reason, and everybody who works with Powerline knows that sometimes Powerline does not work that well, you know. Sometimes you drop something and so on. But in that case, immediately another route is set by the system, and you can continue to operate your network. And the switch is instantaneous. So basically, it's very quick. So changing the route is very quick. So from a user experience, you keep the connectivity. And this is really the problem with Powerline, because the conditions for Powerline are never really stable in time. So this is exactly the purpose of Powerline, to cope with this situation that it's not really stable. And it's true for all technologies operating on Powerline. They have to cope with this. Because of noise, because of saturation, because somebody connects something new, because for some reason, the conditions are not stable. So we reduce the communication time delay, and we improve the communication throughput. Next slide. Okay, so this was about standardization, and the next two slides is about certification. So standardization, like in IEEE, the IEEE standard is 1,600 pages long. It's a book. And you have, if you go through the book, you have so many options, you know. You have, okay, basic options for channels, but you have different MAC services, different type of CSMA. I put some example here, but this is an extended list here. Like file level 1 concatenation. There are many things like this that are defined in the standard, and they are optional. You know? Okay, you can do this. If you, it reads basically, if you want to do this, you do it this way. Okay, good. So it's the same with Wi-Fi. Okay, if you take 802.11, there are plenty of things in it. So basically, the standard itself does not ensure interoperability. It just says if you want to do this, do it this way. Same for security, authentication, encryption. We have several schemes. We can use AES, 128 AES. You can use Camellia. You can use. Okay, there are several options. So basically, this is the job of Nessum certification to ensure interoperability and performance check. Because if you give the standard to someone and tell him, okay, go and implement the standard, you have almost zero chance to have something interoperable with the existing things. Because it's too big. So we have to select basically which features and so on are exactly in the implementation and to test, etc. So we have a connectivity verification test that are defined by Nessum Alliance, and we have a golden implementation. So we have a golden device. So the certified products, the certified subsystem are tested against the golden device to make sure that we have something interoperable. So it's a real test, you know. Can you communicate? Okay. Can you start a network? Is it the same authentication? Is it the same security? Yeah. And then you check. And also, not only interoperability, but also performance. This is important. So when you go through Nessum certification, you have a minimum performance, because performance has been tested. And where to make certification? We have two venues for certifications. One is Panasonic Test House. It is in Fukuoka, Japan. In Panasonic premises, there's a typical Japanese house, I would say. But okay, if you take the picture, it's a house, but inside there's a lot of equipment you don't have in a regular house because you have all the testing equipment. But it looks like a house. It's very nice. And also, it's available at UL in Taiwan. So we have two venues for delivering certification according to this. So this is a certification scheme. Next slide. On top of a certification scheme, which ensure basically interoperability and performance, we are currently working on profiles. And the reason why we are working on profiles, it is that the technology is really flexible. You saw all the channels and all the things like this. So when we promote the technology, we say, okay, look, you take the chipset and you do whatever you like with this. But we are also have to tell the market, okay, for which technology is good for this and to make things easier. So the purpose of a profile, what is a profile? Profile is a list, a minimum list of features to be supported. So we have a big list of features, and we say, for one profile, for example, Smart Gate, we have flexible channel multi-op. So if you buy a product or a chip that meets that is certified for MV Smart Gate profile, you have at minimum all this list of features available in the chip. So it's really, purpose is really to make implementation easy for specific use case for OEM and end users. So instead of going into the details and reviewing all the detailed features, you just say, oh, I want this profile or the other profile, and then we have a preset list of things. So it supplements basically the flexible approach. Flexible approach is nice because you can do whatever you like, but here at least you have some predefined list with predefined profiles. And at the moment we have 3 under development. There are others in consideration, but we have 3 under development. First one is low voltage, medium voltage smart grid. In summary, it is some flexible channels with multi-op. We have a high speed profile, which is flexible channel but single op. So it's really focused on a smaller distance, but really high speed. And the third one is the legacy one, what we call the Ethernet adapters, the old one, which legacy single channel, which is the original standard. We keep it because there are still some product on this. And also, the purpose also is to communicate that we promote the technology for specific use case. Next. Okay, so takeaway for my presentation. Next. So first of all, it's a robust and versatile communication technology that seamlessly bridges the IoT gap. Just one word about bridging the gap. What does it mean? It means 2 things. It means multimedia, so we can use on different media, and you have to see the Nessum technology as a kind of distributed switch. So basically, you transport Ethernet packets. So you have a 100,000 nodes, basically, and with the technology, you can send and receive Ethernet packets. So you can basically seamlessly connect Nessum technology with all other technology that use Ethernet packets, which is now very popular because there's a lot of IP communication. Here it's an Ethernet switch. Next. It's standardized in ITU, so you can buy the standard, you can read the standard, you can participate also in the working group. IEEE working group is still active, so you can bring new ideas, we can develop a new amendment. Good. Next. And finally, it's a certification program to assure interoperability, performance, and security. And we have two main types of certification. It's Nessum wire, when you use on cable, coax, twist pair, core lines, any kind of wire. And Nessum air, which is the wireless version for certification. That's it. Thank you. Next. This is my email address. Yeah. So you can contact me in any way if you have some question. And thank you. Thank you, Scott. Yeah. Oh my gosh. Any? I don't know if we have time for questions. No, probably not because I took more time.
We have a session.
Okay. Yeah. Okay. So, questions or okay, we can talk later. Okay. I have a coffee break. Okay. Thank you.